Hi everyone, welcome back. We're on lesson 17, radicals and solving quadratic equations. Our learning goals for today are to learn to put a radical in simplest form. So radical may be a new term for most of you, and putting it in simplest form as well. And we're also learning to find the exact roots or solutions of a quadratic equation using either the square root method and also using the quadratic formula, which hopefully will be reviewed, but with our little add-on of a radical in simplest form or exact roots. So irrational numbers of the form square root of n are called radicals. The square root symbol, which you know, is called the radical symbol actually. An entire radical has the form the square root of n, square root of some number, whereas a mixed radical has the form a square root of b. So part of the number is under the radical and part is out front. I kind of think of entire and mixed radicals as kind of like mixed and improper fractions, but radicals instead. Okay, that's an analogy, I guess. It's possible to change between entire and mixed radicals. A radical is said to be in simplest form if the number under the radical symbol is not divisible by a perfect square. So rewrite each radical so that it's a mixed radical in simplest form. So square root of 50. You want to rewrite that so it's in the simplest form. And our rule is a radical is said to be in simplest form if the number under the radical symbol is not divisible by a perfect square. Okay, well, what are perfect squares? Well, 1 squared, 1 is a perfect square, but every number is divisible by 1, so we'll go to the next one. So 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. So notice these are all perfect squares. So this one again is 2 squared, 3 squared, 4 squared, 5 squared. That's how I'm getting these numbers. So the next one would be 7 squared, then 8 squared, 9 squared, 10 squared, 11 squared, 12 squared. And that's usually enough of them that we can reduce or simplify most radical expressions. So square root of 50. So in order to rewrite it in simplest form, we want to see if 50 is divisible by a perfect square, but we also want the largest perfect square that it's divisible by. So doesn't go, 4 doesn't go in evenly, 9 doesn't, 16 doesn't, 25 does. And if you go halfway to the number under the radical sign to test that, like the halfway is 2, you don't have to go more than halfway testing. So 25 is the biggest perfect square that divides evenly into 50. So watch this. So if we do root 50, we can actually change that to square root of 25 times 2. 25 being the biggest perfect square that divides evenly into 50. And then using the rule of square roots, we can rewrite that as the square root of 25 times the square root of 2. And then we chose perfect squares because you can take the square root of 25 and that gives you 5. And 5 times root 2 can be written as 5 root 2. So that's kind of the procedure for rewriting a radical so that it's a mixed radical in simplest form. And notice that if we look at the number under the square root sign 2, it's not divisible by any of these perfect square numbers up here. So I also just wanted to show you that if you were to type this into a calculator, square root of 50, you get 7.07 approximately. So approximately 7.07. So if all we've done is change the form, root 50, 5 root 2 should be the same thing. So So again, if you go to your calculator and do 5 times the square root of 2, that should also give you 7.07, and you can see that it does. Okay, so just knowing that these are actually the same, but this one's considered to be in simplest form, 5 root 2. Root 50 is considered to be unsimplified radical. Okay, so that's what we're doing. So we'll move on to the next one, 80. So if you look at 80, for instance, it's divisible by 4. So 4 times 20. But we want the biggest one that divides evenly in. So like 80 divided by 9 doesn't go in evenly. 80 divided by 16 does go in evenly. And if I look at that number 5, so 16 times 5 gives me 80. I know that 5 is not divisible by a perfect square, so I should have found the largest one that divides in evenly. But you could try 25 and 36, remember, until half of 80, and then you're for sure you've got the right one. So we can rewrite the square root of 80 as the square root of 16 times 5, 16 being the largest perfect square that divides evenly into 80. And then we can rewrite that using our radical rules here as root 16 times root 5. But then square root of 16 is 4, because we found a perfect square that divided it evenly. So that becomes 4 root 5. Okay, so again, root 80, if you did that on your calculator, and 4 times root 5 should both give you the same result. Okay, now we're on to square root of 27. Square root of 27, so not divisible by 4 or evenly. 9 goes in, and that is the largest one that goes in. So we can rewrite as root 27 as root of 9 times 3. Root of 9 times root of 3. Square root of 9 is our perfect square. So we've got 3 root 3 is the simplest form of writing the square root of 27. Okay, and moving up to our next 3. If you want to try the next 3, you could pause the video right now and try them on your own and then check back. So root 99, think about it or use your calculator, but 9 is the largest perfect square that divides evenly into 99. And then I can change that to root 9 times root 11. Square root of 9 is 3, so 3 root 11 is simplest form. Root 98. So again, I'm unsure, maybe, so I'm looking up these at my perfect square numbers. 98 divided by 4 doesn't go in evenly, 24.5. 98 divided by 9, no. 16, no. 25, no. 36, I could try. Nope, doesn't go in evenly. 49. Oh, perfect. Okay, so 49 is the largest perfect square that divides evenly into 98. So the square root of 98 can be written as 7 square root of 2. Root 72, this is a good one because 72 is divisible by 4. But it's also divisible by 9, not 16, not 25. It's also divisible by 36, and we want the biggest one. So the biggest perfect square that divides evenly into 72 is 36. And we've got 6 root 2. Okay, so that's the idea. That's how you rewrite a radical so that it's a mixed radical in simplest form. And that's going to come into play when we're solving quadratic equations. Okay, so we've already solved quadratic equations in chapter 1 this year. It's an equation that can be written in the form ax squared plus bx plus c equals 0. There's 3 methods that you learned in grade 10 to find the roots or solutions. So roots and solutions means the same thing of the quadratic equation. Factoring, no, we did not do that yesterday. We'll do that later this week instead. But we have gone over the quadratic formula this year, and we're also going to learn the square root method. We've kind of done it already when we looked at some word problems, and we'll look at it in more detail today. Okay, so our first question. Solve the following quadratic equation, determine the exact solutions in simplest form, then use your calculator to determine the approximate solution. So one thing that this question is going to highlight is the difference between exact solutions and approximate solutions, which is a very important thing that you need to understand the difference between. So based on what we did last week with some of our word problems, you can see that x is only in one spot here. So I could use reverse BEDMAS to get x by itself. So I've got a quadratic equation. I know it's quadratic because I've got x and it's being squared, okay? And the x is only in one spot, so when x is only in one place, you can use reverse BEDMAS. So if I'm going to do that, I would subtract 20 on both sides first. Okay, then I'm going to square root both sides, remembering that I need plus or minus, because there's 2 possible square roots of 28, a positive and a negative. Okay, so then if we look back at our question, solve the following quadratic equation, determine the exact solutions in simplest form. So that's where our reducing our radicals that we just learned about comes in. So what I want to do then is I want to look on this side here and see if I can simplify the square root of 28. And sometimes you'll be able to simplify and sometimes you won't. So if I were able to simplify, there would be a perfect square that divided evenly into 28. So what were those perfect square numbers again? So it was 2 squared, which was 4, 3 squared, which was 9, 4 squared, 16, 25, 36, ... So the biggest one that divides evenly into 28 is 4. So I can rewrite the square root of 28 as the square root of 4 times 7. And I can see that I'm going to do the square root of 4, which will give me the 2, times the square root of 7. Okay? So I've simplified the square root of 28 to this 2 times the square root of 7. They mean the same thing, but this one's considered, 2 root 7 is considered simplified. Okay? And then we still have to add 5 to both sides. So I've got that x equals 5 plus or minus 2 square root of 7. Okay, so what does that actually mean? So that means there's 2 solutions to this quadratic equation, and the exact solutions are that x is equal to 5 plus 2 root 7 and x is equal to 5 minus 2 root 7. And when you're answering a question, it's perfectly fine just to combine them and write that x is equal to 5 plus or minus 2 root 7. But I do want to go over again with you the fact that these would be the exact roots. Okay, so no rounded numbers. These are exactly the solutions. 5 plus 2 root 7 and 5 minus 2 root 7. Sometimes, especially in word problems, they'll want you to also find approximate solutions. And that's where you go to your calculator and you actually type that in. So if you wanted approximate solutions, first of all, you'd put x is approximately equal to, and then you're going to type into your calculator 5 plus 2 times the square root of 7, and you get approximately 10.3 if you round. And then this one, and we want to do clear calculator, 5 minus 2 times the square root of 7 equals, and that's going to give you approximately negative 0.3. So I think in grade 10, you were used to, especially if you got an answer that was not a perfect square, so didn't lead to like x equals 5, for instance. When you had a root, you always found these approximate solutions most often, okay? But in grade 11, the new add-on is we want to find these exact solutions instead, okay? So we're going to save approximate solutions from now on just for word problems, and we're going to focus on being able to give these exact solutions in simplest form, okay? All right, so we're going to continue working with the square root method. We could use the square root method if we complete the square, which I'll show you an example of that as well, and when we would use that. So solve each quadratic equation using the square root method. Express the solutions as exact numbers, so they want the exact solutions, no decimal places, no approximately equals, just the exact numbers in simplest form, okay? All right, so again, if we look at A here, you can see that the x is only in one spot, and we do know it's a quadratic equation because of the squared here. So we can use reverse BEDMAS to solve. So the first thing we would want to do to get x by itself would be to add 7 on both sides. So negative 43 plus 7 is negative 36. Then divide both sides by negative 2. It's going to give me positive 18. Now we can square root both sides. And remember, on the number side, we need our plus or minus for 2 possible solutions. So x plus 4 is going to be positive or negative the square root of 18. So now we want to check and see, can we simplify? Question mark. So if we could simplify the square root of 18, it would mean that one of these numbers, so 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, dot, dot, dot. We want the largest one that divides evenly into 18, and that is 9. So it can be simplified in this case. It won't always be able to be, but we're always going to be able to check and see if it can be. So 9 divides in evenly, biggest perfect square. So I can rewrite 18 as 9 times 2. So plus or minus, so the square root of 9 is 3, but that's still being multiplied by the square root of 2. Okay? Still want to get x by itself, so I'm going to subtract 4 on both sides. And by convention, so 3 root 2 and negative 4 are not like terms if you want to think of it that way, because this one has a root 2 ending and this is a plain number. By convention, you want the plain number to come first. So negative 4 plus or minus 3 root 2. So this would represent, again, 2 solutions. So just so you guys are sure here of what this means, these are 2 solutions. One of them is negative 4 plus 3 root 2, and the other one is negative 4 minus 3 root 2. So that's being given 2 solutions. They're exact, being given exact, no decimal approximations, and they're in simplest form. Because we reduced root 18 to 3 root 2. Okay, so we've got 2 solutions there. We gave them the exact solutions in simplest form, which is what the question asked us to do. Okay, so in part B, it says to use we're still on the same example, so it wants us to use the square root method again, but you can see the x is in more than one position. If it wants you to use the square root method, it must mean that it's easy to complete the square, and that we have the x only located in one position. So we could do that because this one's easy to complete the square. So if we wanted to complete the square on the left side here, we would take half of 6, which is 3, and square it. So that would mean we'd add 9. We also need to subtract 9 so that we've balanced our equation. And then we still have this minus 1 equals 0. But we've created a perfect square trinomial that when we factor it and then combine these two terms here, we end up with a quadratic equation with the x only in one position. Okay? So this is a good method to use if it's very easy to complete the square and turn it into having the x in only one position. I would only do this if the a number was a 1, the b number was something that was easy to divide by 2 and square, didn't create a fraction, okay? Otherwise, I would use the quadratic formula, which is what we're going to look at next. But this one was really easy to do. So then now we're going to use reverse BEDMAS to get x by itself, so we're going to add 10 to both sides. Square root both sides to undo the squared. And then here's where we would look and see, can the square root of 10 be simplified? So if it could be, then it would be divisible by 4, 9, 16. No, it's not divisible by those. So it can't be simplified. So we can just subtract 3 on both sides. Write our -3 first, and then our radical part second. So again, here are our roots. And those are, again, 2 exact roots, which means the same thing as solutions, in simplified form, because root 10 is as simplified as we could get. And those roots are -3 plus the square root of 10 and -3 minus the square root of 10. Okay, so the next method we're going to look at is using the quadratic formula. So this is a more familiar method probably to most of you, and we did work on it in chapter 1 on functions. So find the exact roots. The difference here then again though is we're asking for exact roots, whereas in chapter 1 either the roots worked out perfectly to be integers or we used decimals, approximations. We didn't have to get these exact roots in simplified form. Okay? So again, we're not giving decimal answers here. We're giving our answers will be in terms of roots, or it might work out to be an exact integer value. All right, so again, here you can see we've got an x squared and an x. The x isn't just in one spot, so you can't use reverse BEDMAS, and putting it into vertex form would involve factoring, fractions, etc. So it's better just to use the quadratic formula. So to use the quadratic formula, which I've reminded you what it is up here, we need to know that a is the coefficient in front of the x squared, b is the number in front of x, including the sign, and c is the constant, including the sign. So we're going to start off, I'm going to write out the quadratic formula again. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Then I'm just going to substitute. So negative and then -10. -10 squared minus 4 times 2 times 5 all over 2 times 2. So I remember a couple people asked me what you do with this negative 10. So it's like there's a -1 there and you're multiplying. So it ends up being positive 10. And then again, we were trying with our calculator to always get the number under the square root sign in one step here. And part of that was knowing that it doesn't matter whether we square a positive number or a negative number, we're going to get a positive answer. So I can write in I don't have to worry about the negative sign, 10 squared minus, so there's my minus, 4 times 2 times 5 equals, and it gives me 60. So the number under the square root sign is going to be 60 over 4. Okay, so all of that still looks like first chapter or grade 10 stuff, but now here's where we're gonna, first, if 60 were a perfect square, that would be great. That would mean that, like for instance, 64 is a perfect square. So you get 8, and then that would be great, but 60 is not. So we're not just gonna take the square root of it, because that'll give us a decimal and we want exact answers. So now we're going to ask ourselves, can we simplify the square root of 60? Can we simplify that radical? So if we could, we're going to again look at the perfect square numbers. So 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, etc. And we're going to look for the biggest perfect square that divides evenly into 60. You could try, but it's going to work out to be 4 is the biggest one. So not too exciting, but we can reduce it. So we can rewrite square root of 60 as square root of 4 times, well, what if I'm not sure here? So 60 divided by 4, 15. Sorry about my dogs. Again, if you need to, you don't need to show this next step, but some of you might want to, so you can do root of 4 times root of 15 here. But you should be able to get it down this far. So square root of 4 is 2 root 15 over 4. Now, we've simplified the radical, but believe it or not, our answer is not in simplest form. And that's because 10, 2, which is the coefficient of the radical, and 4 all have a common factor of 2 in them. Meaning I could divide top and bottom by 2, or it's better to think of it as I want a common factor 2 out of the numerator. So if I did that, remember I'm mentally dividing 10 divided by 2 gives me 5. Plus or minus, so 2 root 15, I'll write that off to the side, so 2 root 15 divided by 2 would just give me the root 15 part, all over 4. So now I can look at, I've got 2 multiplied by this radical part, 5 plus or minus root 15 over 4. I can now divide top and bottom by 2, so divide by 2. Divide by 2, and I end up getting 2 divided by 2 is 1, so what's left on the top is 5 plus or minus root 15, and what's left on the bottom is 2. Okay, so again, there's my solution, and that represents 2 exact roots in simplified form. Okay, so you could give your answer like that. That's awesome. Okay, that's perfect. But just for clarification, so you remember if you're typing them in your calculator or whatever, those 2 roots are 5 plus the square root of 15 over 2 and 5 minus the square root of 15 over 2. Okay, some textbooks might divide each piece by 2 as well and write it like that. And you can play around with your calculator and convince yourself that these all mean exactly the same thing. Okay? But again, the green box here is perfect. Those are given, we followed the instructions, we found the exact roots of the quadratic equation, and we answered in simplest form. Okay, next one. So this one, I guess a little bit trying to confuse you, but you should be able to see that a is the number in front of x squared, b is the number in front of x, and c is the constant. So the quadratic formula, substitute, all over 2 times 3 . Okay, then we want to get that number under the square root sign, so 77 squared minus 4 times 3 times 50 is 5,329 over 6. Okay, so again, I want to see, can I simplify the square root of 5,329? So with a number like that's really big, the first thing I would do is just see if it's a perfect square. So I do square root of 5,329 before I start trying out all those other ones. And in this case, it works out. So it is exactly 73. So what happens in that case? So plus or minus 73 over 6. Okay, so that kind of harkens back to a grade 10 question, where now you'd be ready to go into 2 different solutions here. But remember, we want exact answers. So x equals negative 77 plus 73 over 6. And x equals negative 77 minus 73 all over 6. So that's going to be negative 4 over 6. But that reduces to negative 2/3. And then for this one, negative 77 minus 73 is negative 150 over 6, which is exactly negative 25. So in this case, again, we have 2 exact solutions. 2 exact roots or solutions means the same thing. But these ones don't have radical parts because it turned out that the square root of 5,329 was 73. So 5,329 was a perfect square, 73 squared. So that ended up giving us a fraction and an integer for our solutions. Okay. All right. So we've looked at a bunch of different questions that have different outcomes. This is probably the one that people will have the toughest time with because it has that factoring step in it. So we common factored here. So when you're doing the practice, be careful to try to look out for that first of all, and then try it, and then look over the solutions carefully. Okay. So our last question today. So all quadratic equations can be solved using the quadratic formula. The method of factoring, which we're going to talk about later this week, can be used when the polynomial is factorable. The method of completing the square should be used when it's relatively easy to change from standard form to vertex form. So what did we look at today? We looked at the quadratic formula, and we looked at the completing the square or square root method. Okay? So those are the 2 methods we're going to do then to show that the roots of x squared minus 6x plus 2 equals 0 are in fact x equals 3 plus or minus root 7. So let's kind of divide our page up to show our 2 methods here. So method 1 and method 2. So maybe method 1 for us is going to be the quadratic formula. So we would be noting that A is 1, B is -6, and C is 2. And then we're going to use the quadratic formula. Substitute. So -6 plus or minus the square root of -6 squared minus 4 times 1 times 2 all over 2 times 1. And then under the square root sign then, so that's going to be 6 squared minus 4 times 1 times 2, which gives me 28 over 2. Now we're going to check and see, can the square root of 28 be simplified? Yes. So the biggest perfect square that divides evenly into 28 is 4. So we can rewrite the square root of 28 as 2 root 7. So we've done a lot of simplifying, but this is one of those cases where we have to factor because 6, 2, and 2 all have a common factor of 2. So we want to common factor 2 in the numerator. So 6 divided by 2 is 3. 2 root 7 divided by 2 is just root 7 over 2. And then we can do 2 divided by 2 gives me 1. Ending up with x equals 3 plus or minus root 7, which if you look at the beginning question, it wanted me to use 2 methods to show that the roots of the quadratic equation, or the solutions, were x equals 3 plus or minus root 7. So we did that using the quadratic formula. Again, these are 2 exact roots in simplified form. Okay. All right, method 2 then. So the other one that we looked at today was using completing the square to make it so x is only in one position, and then use reverse BEDMAS. So if I'm going to do that, I'm taking half of 6, which is 3, squaring it, that's 9, add 9, subtract 9, add 2 equals 0. Here's my perfect square trinomial, which factors to give me x minus 3 squared. Minus 9 plus 2 is minus 7. So now x is only in one spot, so I can use reverse BEDMAS to solve. So I'm going to add 7 to both sides. Square root both sides. Don't forget the plus or minus on the right. Then I would check to see if root 7 could be simplified. And that's a no. Okay, so 7 is not divisible by a perfect square. Add 3 to both sides. And I get x equals 3 plus or minus root 7, which is what I was trying to prove again. So I've used 2 methods to get the same 2 exact roots in simplified form. Okay? All right, so our success criteria for today are that we could change a radical from entire form to a mixed radical and simplest form, and that we can find the exact solutions or roots of a quadratic equation using the square root method or by using the quadratic formula. All right, thank you very much.